So today we're gonna be doing um integration, but for like um volumes. Volumes. It's a concept. Yeah, it's a concept, and I just want to make this video so that I don't forget. Because class, I did not understand for a while until I got it. So I want to make this so that if I ever forget, I can come back. Integration for volumes. Keep in mind this is not volume of revolutions. That's what I thought when I went into class. Volume of revolutions. Not volume of revolutions. Okay. So we're going to do two questions. We're going to prove that, first of all, the volume of a cone is equal to 1/3 pi r squared h, and that we're going to prove the volume of a sphere, oh, we're going to prove that the volume of that is equal to 4/3 pi r cubed. Okay, so let's do this. So if we think of our cone and we put it on a axis like this, let's just give it an over z. And let's put it on the axis like this, and we're gonna say like bam, that, like that. So what do we have is at point 0, that's the tip of the point. This is the height of the cone, right? H here is just the value of this length from here to here, right? So h is there. This is the x-axis, by the way. This is the y-axis, or we can call it fx. And we can and this is r. This is r. This height. And what does this height mean? It means that at when x is equal to h, when x is equal to h, then y is equal to r, right? Because at x equals h, y is up here. And keep in mind that it's just this length here, technically, and it just crosses over to this point at h, and then it crosses over to different points. So we can think of it like that. So I'm going to put it back at this, just to make the diagram a bit easier to look at. So that's r right there. Okay, and now what we got to do is we got to think in terms of, today in class, we learned that like you're supposed to split shapes into different slices. So for example, like if we split the cone into like shapes like this, oops, like split it into pieces like this, just keep splitting it. You get what I mean? But then like if you split it enough, right? Let's look at it from sideways. If you split it enough, you can think of these as rectangles, right? And these rectangles, all you have to do, technically it's a cube. So a cube, or like a cuboid, right? So if you imagine these were cuboids, actually, it's not a cuboid, it's a cylinder. We split it into a cylinder. That's my bad. We're splitting it into cylinders. So if we take it enough, these sloped edges become straight lines, right? You can approximate them to be like this. And now if it's a straight line, instead of being a piece that's kind of like this, for example, it turns into a piece that looks like this. And that's just a cylinder. And a cylinder, we know the equation for. The cylinder is just R, and this is H, and the volume of a cylinder is just R squared, pi R squared, the area of the circle, times by H. It's this. So what we just got to do is split the triangle, split the cone into so much slices that it turns into cylinders, which then we can just use this. So how are we going to do that? Okay. We're going to use dx. Okay, let me explain. So if we have this graph here, Okay, this is x, this is y. So let's say from this point to this point, what's this length, right? When we split it up, this is delta x. This length here. This length is delta x, or called dx. And this is the same equal length across all these slices. These are just dx's. And so this triangle is just made of cylinders that are multiplied by dx. And the area of the cylinders, the radius, sorry, because at each point there's a different radius, right? This is, let's call this radius, I don't know what this, maybe this is radius 10. This one is the 20th radius, right? So at each different radius, it has the same height, right? If we extrapolate, let's take R20 out. So it will technically look like this in 3D, right? So dx is its height, or delta x is its height, but then the r, this is R20, right? And then that one, R10 would definitely be smaller. So you get my idea? So we just need to add these together. So how do we do this? We do a summation. So work with me now. So first of all, we got to find a general equation for r at any x, right? At any x. What is r going to be? So I'm going to do like this. I'm going to draw it again, but in 2D. Okay. So at point H, y, remember this is x, this is y. So when x equals h, then y equals r. So this height is r. So we can think of this as an equation where it's some function of this. So at here, right, it's following this in some way. At here, it's following this in some way. So there's some correlation between h, r, and x. So how do we get that, right? How do we get that? The idea is that if I take this triangle, so this triangle here, the large one, it has a ratio, I'm going to draw a new one. It has a ratio of r to h, right? And I want to find a general form of this. So let's just imagine there's a smaller triangle and there's a form of y to x. What's the ratio of y to x? Well, y, if we think about it, y to x is the same as r to h. So we just say y divided by x, right? Let's say if this was 1 and 2 and this was 2 and 4, 2 divided by 4 is the same as 1 divided by 2. Yes, yeah. 2 divided by 4 is the same as 1 divided by 2. So we can just say that y over x is equal to r over h because they're in a similar ratio. Therefore, y is equal to rx over h. And we can just split this as r over h multiplied by x. And you might recognize this as the form, y equals mx plus c, where m is equal to r over h and c is equal to 0, right? That makes sense. This is just a straight line. So if we think in terms of ratios like this, we can find the ratio between y and x of every point on the triangle. And now we can just find the radius at any point x, right? So now we have a general formula for what the radius at each point is. Remember that R10, it just means the y value at the 10th dx. R10, I'm gonna write it down just in case I'm confusing. Let's say R10 is just the y value when or at the, let's say at the 10th dx. Just think of it like that, at the 10th delta x. So remember, yeah, and the reason why is you can just trace it back here, and it's just the correlation between this line and this thing, and you just go sideways. So technically, it doesn't even exist. It doesn't exist here. It exists on the graph. It exists here. But apart from that, you don't need to think about that right now. But we just need to think we just find the general formula for the r of each of these slices, the different slices. As long as you have the x value, we can now find the radius of that slice, which is this equation. Yeah. So we're just saying now, let me rewrite everything, that the y equals r, is it r over h? I think so. Yep, r over h of x, which means that the radius at any point x is equal to r over h multiplied by that point x. Okay. So now we just gotta think. We found the radius, right? Remember, what's the equation for a cylinder? The volume of a cylinder is equal to pi multiplied by the radius of that point multiplied by h. I'm going to rewrite this down here, okay? The volume of a cylinder is equal to pi multiplied by the radius of that point squared, then multiplied by the height. What is our, oh, wait, sorry, give me a second. And then all we gotta do is do this for every single little slice of the cone. Where's my diagram? Every single slice of the cone. We just do that until the end of the cone, and then we have the full volume of the cone. So what's a way to write that? If we wanted to write, actually, let me just write. So therefore, we can equate this. I'm going to use the variables we found. We can say volume is equal to pi multiplied by the radius. Okay, where is it? The radius of any point x, right? The radius of any point x. So we need the radius of any point x. So here, okay, I'll do this. So if we have the radius of any point x, and we know the equation for the general volume of any cylinder, therefore the volume of any, let's call it slice, of any cylindrical slice, the volume of any cylindrical slice of the cone is equal to, and we just substitute the radius of any point x, of any point of the curve, of the cone. Oh shit, I forgot to write, okay. Of any point x, oh, at any point x, is equal to, let's say that again, the volume of any cylindrical slice of the cone at any point x is equal to pi multiplied by the radius at that point x. The radius at that point x is given here, r over h multiplied by x, right? That's the radius, remember? This is the radius of any point at any point x is equal to this. And remember that this radius is the big radius at the end of the cone. This is the r there denotes the radius here. And technically this is just y. Technically y is equal to here, and y is equal to the radius at any point because it's the height of the graph at that point. Okay. So we need the radius at any point. So we're at the r squared. So we need the r, the radius at that point, which is r over h, the big radius over h, times by x and radius squared, times by height. So the volume of one slice at any point x is given by this. All we need to do is sum it up. So therefore, the total area of the cone is given by, all we have to do is summation. So we're going to use the sigma notation first. Sigma notation. So we have the first slice. So that is x equals 1, right? Or whatever the smallest thing is. And then we're going to h when x equals h, right? And then we're going to the summation of pi multiplied by r over h multiplied by x of squared multiplied by h. And what is h in this case? What is h? Remember, What is the height of the slice? Dx. The height of the slice is dx. So what's going on? Why does this look so familiar? Why is that dx at the end? Well, we can just rewrite the summation as this. Well, technically it should be 0, that's my bad. But we can just write the summation symbol into the integral symbol, which is just an s, which means summation can go from 0 to h, multiplied by pi, multiplied by r over h, x all of this squared, dx. Because the dx is getting multiplied there. So this is the idea of the integral sign, and this is the idea of kind of splitting things into slices and finding its volume. You end up with this. This is just the running total, kind of. It's the running total where you can have a flexible x, right? Because x goes from 0 to all the way to h. So the reason, that's why we need to use something like this. And then this just kind of limits it. This just does it infinite times so that you get really small rectangles, so that it's perfect cylinders, and then you can add it all together. So we're going to do the integration for this now. This is not an integration video. This is the finding volume size video. So you can skip this part because I'm just going to be doing the math. Okay, so I'll do the math now. You can skip this part. So we have pi here. Let's split this up. So we have pi times r squared over h squared multiplied by x squared dx. And because these are constants, I'm going to be taking them out. So I take them out here. Pi r squared over h squared. Outside of the summation h. And then x squared remains inside. Now I'm going to do this is equal to this. H squared multiplied by and x squared, we increase the power by 1 and divide by the new power. Increase power 1 is 3, so x cubed, divide by the new power is 1/3. Because you divide by 3, and this is from 0 to h. So technically, this is 1/3 h, right? We put the h where the x is, cubed, minus 1/3 0 cubed. This is just equal to 0, right? Because 0 cubed is 0, 1/3 multiplied by 0 is 0. So this is equal to h cubed. And all we have to do is simplify this. So I'm going to put it all together first. R cubed. H cubed over 3h squared. Let's just check. Pi r squared. H cubed over 3h squared. All right, now h squared cancels with 3. Oh, let's just keep everything in there. Cancel out this. And then now we have pi r squared h over 3. Or in other words, 1/3 pi r squared h. Which is exactly what we went with. Pi 1/3 pi r squared h. See? So this is how we can do. It's generally this idea of dx here, which is something I really didn't know before. I didn't know that dx can be used as a length. I thought it's just part of the integral sign, but no, it's actually a crucial function. You're actually multiplying with dx. So that's why it's actually a thing here. You're multiplying with dx. So yeah. So if there's any questions, you guys can ask in the comments. Just skip the second if I'm thinking too much. Just skip this section if I'm thinking too much. I just need to think if I'm missing any explanations. For me, it's just the kind of what is the general R, right? And the general R doesn't mean like the big radius at the end. Remember, there's a big radius at point H, but along points here, there's another, like, let's say R20 is right here, right? And there really isn't 20 R's. There's like infinite R's because it's a summation symbol and it's like, it's infinite. It splits it really small. But this is R20 and this is like R10, right? So you can see how at every point, new other point, let's say like at when x equals like, for example, like 1, if say h is 10, right? Well, 1 is here. Then this point goes up here. This is R, let's say this is R1. And R1 has this, right? R1 is this height, which is actually represented by y. So that is why we say we use y equals. We say y equals r over hx is because this y value here, whatever the y value is, right? That's the intermediary radius. this r here is not the radius of any point here. It's just the final number here of any cone, right? Any cone that we apply this equation to. So that's why the r stays there. So for me, that's kind of the big breaking points, is that I need to realize that I'm looking for the general r along the curve, and I recognize that actually the length is dx, and we're multiplying by dx, and that's why we can put together an equation through these kind of sets of logic. Also took me a lot of time. So that's kind of what's really cool. Okay, now we're going to do a sphere. So we're going to prove that a sphere's volume, right? A sphere's volume is equal to 4 over 3 pi r cubed. Okay. So I'm gonna go faster than the cone because I wanted to establish fundamentals, but now that we're on this pace, it should be okay now. So I'm just gonna draw a sphere on here, and I'm gonna show you how I lay it out. Okay. Oh, keep ink. I'm gonna lay it out like this, and this center point goes through here. And maybe I'll shade in the bottom just so you guys can see. Okay, does that make sense? And this point here is going to be our origin, so that's 0. And this point here is going to be the radius. So I'm going to show you how we're going to split it, right? We're going to split it in a sense where we have just one hemisphere. I want you to think in terms of one hemisphere first. So we're going to have it like this. We're just going to have this hemisphere here. Oh shit. Okay. We're just going to have this hemisphere here. Keep ink. And it goes all the way out here. So if you can imagine like a hemisphere, and it's like this. Oh my god. Like that. Like that. Crap. Oh, it's like here. Yeah, that's why it was so confusing. And I'll color it in just a bit so you can see. But it's just half a cone. It's just half a sphere. And it's going from this point here. I should use a different color. Wow, I suck. It's going from this point here to this point. That's radius, right? Because it's going from this point here to this point. That's another radius. It's going from here to here on this point. That's radius. But there's nothing at the back. Nothing at the back. Okay, just a hemisphere. So how are we going to do this? I'm going to plot it on a 2D. So you can imagine this now, right? You can imagine that. I'm just going to plot it on a 2D thing like this. Just a hemisphere first. This is X, this is Y. And I'm going to split this thing, again, into stuff like this. Just into many of these things. Let's remind ourselves the width of each of these rectangles is the height of these cylinders. Remember, when we do this, we split it into little cylinders like this, and a smaller one, and smaller one. You get my idea, right? We're splitting it into that. The height of each of these is going to be delta x, or dx, which is what we put at the end of the integral sign. All right, remember this, guys. Okay, and now remember the steps. Now we just need to find, actually I'm going to label on here, this is 0.0. This already is the radius. The default radius, the radius of the sphere, I'm going to write it like this, radius of sphere is there, is that height there. Hopefully that purple is a little bit more visible for you guys to see. Let's do it a bit thick like this. Oh my god. Okay. That's the radius of the sphere. But we also want to find a general equation for this height, right? Because if we need to know the radius of this one to be able to find its volume, because remember the volume is equal to pi r squared times height, right? For any cylinder. Same for any of these. So we need to find this radius, which is, let's call this radius big, right? It's not as big. The radius of the sphere is the biggest, but this is radius big. This is radius medium, and this is radius small. We need a single equation to relate our x coordinate, which is just the point on the circle, like a point on the central axis, to the radius of around it, right? So how do we find the equation for this, right? For any point, like this point, the equation for this point, only if we have x. Yep, we're trying to find y. Technically, they're y. So let's call this y. These are the different y's. Y big, y medium, y small. Remember, they just correlate to the radius here. We need to find that based on the radius of this. We're going to use that and the x, right? We only have those two things. So how are we going to find it? Well, we just need to find a general equation that links them. So let's try to think of any kind of thing. Let's draw this out. And let's just try to connect these. So obviously we have our origin here. We have, let's say we want to find the height of this. This is just a random y value that represents, let's say y r big, right? A y value. This is y equals, right? This y equals, what is it equal to? So what is this height? What is this length? This length is x, right? Because that's the x value. This is the length of x. So I'm gonna use blue for this. This length right here is x. Okay, and what is this length here? Okay, well, any length here, that's just the radius of the sphere, right? So radius of sphere. Okay, so now we have a triangle. It's a right angle triangle. So if we use Pythagoras' theorem, technically radius of sphere is always going to be equal to whatever the x coordinate is squared. Forgot the equation here. Radius of sphere squared is equal to whatever the x coordinate is plus squared plus the corresponding radius at that point, which is the y value squared, right? So if we rearrange this, y squared would be equal to r squared minus x squared. Let me just check. Yes, it is. And then y would be equal to the square root of r squared minus x squared. So here, therefore, the y, which is the radius at any point x, right? At any point x, because y here, okay, if x was here, then this would be y, right? So y is the radius at any point x is equal to, just look down here, the square root of the radius of sphere squared minus the x squared. All right. So now we have this. And we've found the function for the radius at any point x. Okay, so now let's look at these. Remember, what's the volume of one of this? The volume of one of these cylinders, of any of these cylinders, is pi times r squared. R is this thing, and in this case we denote it as y because it's just the y value here, right? The radius at any point x. R big is just the y value at the x value that gives r big. So this is just y. So okay, r big times height. So I'm going to rewrite it down here. Let's write it like this. Volume of any cylinder is equal to the pi r squared. Remember, that's the area multiplied by its height. Remember, do you remember what this is? It's dx or delta x, right? Okay, so now we write the volume of any slice, any cylindrical slice at x, right? Any cylindrical slice at x. That here, this is the volume of any cylindrical slice of x is equal to the pi multiplied by the radius at point x, which is this one. So this is equals to y. Let's just say y first, because remember y is the radius at any point x. So pi multiplied by the radius squared multiplied by the height of the cylinder, which remember is delta x or dx. Then let's put it out. So let's expand y. Let's substitute what y equals. So y equals this. That's a square root. So we're just going to open that square. We're going to open that square, which is just, I'm going to keep this r in purple. Radius of sphere squared minus the x squared. multiplied by dx. Okay, and now we just need to summate it. We just need to sum all these little cylinders up. We just need to sum it all up to make a hemisphere. So therefore, the volume of sphere, sounds like a helicopter, volume of the sphere, and remember, we're only doing a hemisphere. How much hemispheres are in a sphere? 2. So we need 2 multiplied by the volume of the hemisphere we're going to do. Well, actually, no, let's do this. Volume of hemisphere first. Let's just keep your guys' confusion away. Volume of hemisphere is the summation of all the slices that we found, which is from 0 to, let's check again, from R, right? From 0 to R. Because remember, this length is R as well. This here, x equals R. So we need from 0 to radius. Remember, this is the radius of the sphere. The summation of that and of our equation. So pi multiplied by the radius squared of any cylinder, which is just r. Let's keep the r purple. R squared minus x squared dx. Right? And this is looking a lot more simple. So let's take r out. Let's take pi out. So we have 0. R pi is outside, and we have, so what we have now is r squared minus x squared dx. And now let's just do integration. So what this turns out to be is x multiplied by, okay, so r squared is just technically r squared multiplied by r squared multiplied by x to the power of 0, right? Because r is a constant, it's just the radius of the sphere. So then so that just integrates into r squared x because the x is 0, increase the power by 1, and then this one, so x increase the power by 1 is x cubed. The divide by the new power is this one, and this is from 0 to r. 0 to r, and let's just do it really quick. Pi multiplied by, so we have r squared, we substitute r into x, so multiplied by another r, minus 1/3, put in r, and then we're going to cube it, and technically this minus this whole thing, right, minus is 0 substituted into r, 0 substituted into here, but that turns out to be 0, so we're basically minusing 0, so there's no point doing that. Let's put that back. Therefore, we have this equation. So now we just have, let's do it really quick inside first. So we have r cubed minus 1/3 r cubed, and that. So let's do the math inside, multiplied by r cubed. So that's technically 3r cubed over 3 minus 1/3, 1r cubed over 3. So that's just r cubed over 3. Then that gives us pi, just pi multiplied by 2r cubed over 3, which gives us 2/3 pi r cubed. Okay? And remember, we're doing the volume of a hemisphere. How much hemispheres in a sphere? One sphere equals 2 hemisphere. So all I have to do is take the volume of that, multiply by 2. So if we have 2/3 pi r cubed, we multiply by 2, what does that equal to? 4/3 pi r cubed. There we go. And that's our equation. All right, guys, thank you so much for watching. That took me a while to make, but hopefully that is really helpful to you guys. All right. Yeah, that is curves here, 4/3 pi r cubed. Thanks for keeping with my channel. I know it's been like a year since I uploaded, so really appreciate everyone keeping watch, or maybe it's just me watching. That's also okay. I'm glad I could be of use to at least myself and hopefully to you guys as well. So thank you so much. See you guys next time.